Right, Master of Science students in SCH503. Um, Let us proceed from where we left in this large topic on kinetics. Um, as you can see from the board here, I want to look at mention something about mechanisms and ways of determining them. Okay, so to start with, you're going to say there are three major types uh, of, of mechanisms. I want to see whether the board is very, very clear. Whiteboard, just wait a minute. Good, good, good. I think it was, the top was not very, very clear. Just wait a minute, sorry. Okay, good. So there are three major types of mechanisms. No, type of what I may call chemical reactions. Yeah, not mechanisms, but there are many types of mechanisms. There are three types of chemical reactions, and one is ionic, where you are forming cations and anions, and that is the majority of the reactions that you've been dealing with nucleophiles, electrophiles, all those intermediates, and in this type of reaction, the bond breaks heterolytically. It means that that if a bond has got shared electrons like a covalent bond, then when it breaks, like the one which like the living groups retains the two electrons, and then you've got one of the other one which was bonding in that covalent bond being left with a positive charge. That's the majority of the reactions that you're dealing with. And in this type of reaction is where there is a difference in electronegativity between the bonding atoms. Like in this case, you've got between oxygen and hydrogen, between carbon and oxygen and the rest. Yeah. So in this case, there is difference in electronegativity. The other type of reaction is the homolytic, whereby a bond breaks in such a way that a covalent bond in which each of the two bonding electrons, no, each of the two bonding groups or atoms uh, leaves with one electron. So that one is leaves something called gives something called a free radical. A free radical is where um, uh, it's just shown in general. Maybe you've got an atom and then there is a single dot. Even though that may not be the only electron on that one, there may be other electrons, but the others are probably they're going to be bonded electrons. No, they're going to be what you call electron pairs. But in this case, this the unshared electron is just being shown for simplicity case as a single electron. That's called a free radical. Okay. Then there is a third major type of chemical reaction, which we are going to cover. This is the last topic which we are going to be dealing with, and it is in the syllabus. It's called pericyclic type of reactions. Huh? Now, this is a type of reaction in which there are no intermediates. Are you okay? In this case, you say the intermediates, if you're talking about ionic type of reactions, you can form carbocations and anions, and in this case, you can be able to detect them with whatever equipment and the rest, yeah? Or something like free radical, it's possible to actually detect and the rest. But there's a certain third type of reaction in which we are saying there are no intermediate, yeah? So it's a very it may be say, is it a is it a rare type of reaction? No, this is in fact pericyclic type of reactions are widely uh, they occur widely in nature. Like these are the type of reactions uh, that occur. For example, just say, hey, there is the sun there. You want to do what? You want to go and sit in the sun, and then oh, your body is making vitamin D. Yeah, that is That's a type of pericyclic reaction. But also, um, these are the type of reaction which you're going to see. They're going to be catalyzed by either heat, but mostly by the ultraviolet or maybe visible light, but at a higher frequency. What happens is that a compound with double bonds can absorb energy and is going to break and do type of reactions. This is now where you're going to be told you've got medicine. Please keep this medicine in a dark bottle, or maybe so that uh, reactions do not occur. The type of reaction that can occur, this one's called pericyclic type of reactions. If you've got something like a solvent bottle, it is kept in a dark bottle so that uh, the reagent does not decompose because of pericyclic type of reaction. You're going to see that pericyclic type of reactions are very, 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 very common, and you're going to see uh, the mechanism for this type of reactions, and you're going to see because of no intermediate, the electrons behave differently to what we've been knowing about the movement of electrons. Yeah, you're going to see the behavior or the nature of the electron uh, will be the other. Okay, okay. Perhaps I may just let the cat out of the bag. Yeah, that the the electrons or the photon can have got a mass, and they also move in waves. Yeah. So in this case, what we've been dealing with up to now have been electrons as particles. But you're going to see, hey, uh, that electrons can also uh, uh, move as waves. Yeah. So that you're going to see in this case, we'll be talking about electrons being in orbitals and the rest. So the pericyclic type of reactions are going to make use of the nature of electrons as waves as opposed to particles. So you can only explain them by looking at electrons as waves, as not as particles. So in this case, we'll be talking about electrons being in those shaded orbitals, like p orbitals shaded, and the bottom not being shaded, and the rest. Yeah, to be able to really understand the chemistry of the pericyclic type of reaction. Not no mathematics as such, just simple chemistry, a lot of geometry on just trying to show the shading, these kind of things, interaction between orbitals. Yeah, as opposed to in the other case, like in the homolytic and the heterolytic, you're only showing electron as a single, or like a heterolytic, like a lone pair in which there is a curly arrow. Yeah, are you seeing the different nature of the same particle? I mean, of the same. Now, I don't want to call it the particle now. In this case, you're calling it a particle, but in this other case, you're calling it a wave. Yeah. But anyway, we're going to come to that one. So those are the three major type of reactions. Now, um, you've got a reaction. Now, for you to be able to predict whether that that reaction can occur with similar type of compounds. Like in this case, you've got to say, hey, you've determined that the compound which reacted was an acid, and probably another one was an alcohol. You understand? So for you to know whether maybe what if I was to add one extra carbon atom to this other carboxylic acid, to be able to know whether the similar or homologs are going to react with the same starting material, you've got to study something called mechanisms. Yeah, mechanisms, and mechanism is a way of explaining, reasoning that this reaction has taken place via this method. And even if I have not made this, provided this is the nature, this is something which you call the functional group, and it's going to react with this other functional group to give this product. But as you're going to realize, mechanisms can be wrong. or they can have certain limitations. They may only happen probably under certain conditions, maybe heat, maybe when the concentration is a certain level or whatever. But in certain cases, the reaction may not occur under those conditions. So you're going to see uh, in another uh, topic called the Hammett equation that you're dealing with the same reaction conditions, but you but the mechanism can change. So there is a certain type of this plot which you're going to call the Hammett plot, which can tell you, hey, in this case, uh, the mechanism is the same, but the rate determining step probably has changed. Or in this case, hey, this plot is telling you the mechanism, the reaction is the same, uh, but the mechanism has changed. Are you understanding? But once again, you're going to see there's a way in which you can plot the experimental data, and then it can be pinpoint here. The mechanism has changed. So what are the methods for determining mechanisms so that you can now be able to say, hey, I think this is the mechanism I'm talking about. The most obvious one, and the one which obviously it can be wrong, is identification of the product. So that you're going to say, if you're dealing with uh, with probably an acid and an alcohol, and then I put sulfuric acid and I'm heating, and I'm only going to get ester plus water, then then the the mechanism has got to be that this is where the nucleophile from one of the two reagents is going to act as the nucleophile is going to attack here, based on what you know about the electron density and something like that. Yeah. So identification of the product. If you know the product, then you can say uh, this is likely to be the most probable mechanism in which that reaction is going to take place. But that is not always true. So there are other methods that try to pinpoint as to the mechanism, and uh, and the most obvious one, or the most widely one, is try to see um, if you're talking about a mechanism, then I've got to determine an intermediate. What you're going to see is this. Even if I'm going to say, for example, there is this acid plus this alcohol, they are going to give an ester plus water. What you're going to see is that is is that uh, the reactions may not be explained by just say there is this what there's this reagent and this reagent, they are going to give exclusively to give the product. They may give the starting material may probably decompose to give an intermediate, and then that intermediate may react with the second reagent to give probably a third intermediate, and probably a fourth one, and the rest, and then eventually all those things, those intermediates may react in the solution to give the product. Are you okay on that? So that in this case, the presence of an intermediate can show conclusively that that the reaction is proceeding via that mechanism. And this is where later we're going to see the kinetic evidence. It makes use of the fact that you need to be sure about the type of intermediate that you are going to be, which you're going to be. You need to be. I mean, the kinetic evidence makes use of uh, you proposing, for example, there's this intermediate that you're likely to form, and then through the uh, through the experimental data, then you're going to probably do what? Eliminate a certain intermediate by, or certain reagent, by plotting things like, if I'm going to hold the other reagents constant, and then I vary this, And then I realized, hey, this thing is not varying by this one, by things called zero order faster than the second order. I'm sorry, I'm really going this side, but that's where you're going to say, if this reaction is not dependent on the concentration of this one, then it is zero order related to this one, and therefore going to say, hey, this mechanism which I was proposing is wrong. Yeah. All right. So the thing is, there are, in trying to look at the presence of an intermediate, there are intermediates that you can actually excuse me. There's some intermediates that you can actually detect with an instrument, but there's some intermediates which, once you probably remove the solvent, then that intermediate vanishes. But you can try to trap that intermediate, like an inolet, for example, inolet, yeah, by attaching another element which will form a very strong bond with, like in this case, with an oxygen. In this case, what they usually attach is something like a silicon to the oxygen, yeah. So you're going to form uh, siloxy ethers, something like that one. So just like silicates, yeah, these are very stable, like the sand, yeah. So if you're going to attach, there's usually a strong bond between oxygen and silicon, yeah. Silicon is on the same group as carbon, yeah. So if you're now going to trap an oxygen ion with silicon, then that bond between oxygen and silicon cannot change. So you can now be able to isolate that intermediate, for example, like that enol as a siloxy ether, for example. So that in this case you can say, hey, this reaction proceeds by an inolet. I've been able to trap this intermediate by adding this reagent, and therefore this reaction has been stopped in this intermediate. You understand? So that is called the trapping of the intermediate. Or sometimes some intermediates may be stable enough to be isolated. Yeah. Um, this is not where we are actually forming ions, but some reactions may proceed via an intermediate, and then that intermediate can rearrange, for example, to give uh, the final product. So you can be able to determine to isolate uh, an intermediate, for example, by using the nuclear magnetic resonance spectroscopy method. Yeah, in this case, you can say, if I can isolate this one, or something like, even something like a mass spectrometer. Yeah, if you can determine the mass to the fourth decimal place, then you can be sure only the combination of certain carbon, hydrogen, oxygen, and whatever. Because if you're going to use high resolution mass spectrometer, then you can just only a certain intermediate is going to have a certain molecular ion peak, yeah. So that in that case, if I isolate that one, then I can be sure that is the intermediate that was actually formed, yeah. So spectroscopy methods can be used for knowing the presence of an intermediate. Another way of knowing whether the mechanism that's the mechanism through an intermediate, what you do is you may try to say, hey, if this reaction is proceeding by this intermediate, and this is something which you're going to look at later, uh, because after this we'll look at acids and bases and equilibrium. You're going to see, if I'm going to inject maybe a certain intermediate which I think is going to be formed, then that may affect something called an equilibrium, whether the equilibrium can be shifted towards a certain material or the product, and then that product, that intermediate suspected intermediate which you have added, is going to be consumed in that reaction to give probably the product or the certain material, yeah, as opposed to it being remaining unchanged in the reaction. So in this case, if you're going to add a suspected intermediate that can increase the concentration of the product or the starting material that you can. So yes, this reaction is proceeding via this intermediate. Okay. The other one is isotopic labeling. By now, I think you know what are isotopes. Yeah. Uh, like if I talk about like hydrogen, yeah, there there is the hydrogen, there is the deuterium, and then there is the tritium. What are they changing? The 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 number of the protons and the electrons is the same, and therefore the charge is not changed. But what we are changing is the number of neutrons. Yeah, yeah. Like for tritium has got three. Is it two neutrons? And deuterium has got one one neutron. And as you know, what the isotope does is to increase the molecular mass. That is, the molecular mass is made by the total number of uh, uh, for the neutron and the proton. Yeah. Okay. So these ones have made a lot of change in understanding mechanism, especially if we're talking about like the one you have talked about, like the hydrolysis of an ester to form a carboxylic acid plus an alcohol. Yeah. Um, I'm really sorry I may not show the mechanism here, but scientists had said there are two areas in which the alcohol can attack in the carboxylic acid. Either the oxygen attached to the R group after the carbonyl group. If I'm talking about like CH3, CO, O, and then maybe I've got an R group. So that if I'm talking about like the like the alcohol, like R prime, there are two areas in which it can either attack there, or maybe the bond can actually break this other side here. Yeah. But once again, by by actually by actually changing that oxygen from oxygen 16 to probably oxygen 18, by putting a radioactive oxygen there, then if that radioactivity is detected in one of the products, then you know, hey, this is actually where the bond is breaking and not this other part. Yeah. So through the isotope, you can be able to now know exactly where the bond is breaking, and this is what has been used in in tracing how pesticides and other chemicals are absorbed in plants. Isotopic labeling is a very, 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 I'm using very, very important aspect of understanding the mechanism. Yeah, really knowing exactly where the bond is actually breaking. Isotopic labeling, but it can be expensive, and it can be tricky, and you cannot carry it out as a, especially at master's level, without requiring license, because in this case, if you're going to make use of radioisotopes like what carbon 14 and other radioactive isotopes, then you require permission from the uh, I think a radiology laboratory to be able to actually carry out those tests to avoid the harmful radiation, beta and gamma radiations from probably entering into your body or other people. So this one gives a lot of information, but it's not widely available for most people because of its health risk. Yeah, making use of radioactivity. Yeah, and you know, radioactivity it will lead to radiation sickness, cancer, leukemia, cancer of the blood, and everything and the rest. So it's a good method, but it is risky. It's a good method, but it's risky. Uh-huh. Now, before we come to the kinetic evidence, I need to mention about what? About stoichemical evidence. Now, this is now where um, uh, certain starting materials uh, may choose a certain mechanism depending on the condition in which you are doing, or maybe the pH of the solution can actually change, and that can actually uh, favor a certain mechanism over another one. For example, if if it's going to be if the medium is going to be nonpolar, like nonpolar, you're dealing in what? Like if you're dealing with a nonpolar solvent, like uh, uh, like doing a reaction in petroleum ether, like which other one, as opposed to putting it in polar solvents like methanol and acetone and dichloromethane and the rest, which have got polar charges. So if if there is polarity, then you are going to know that the mechanism is likely to be something like the SN1 as opposed to SN2, where there is just displacement without worrying about stability of the intermediate. In this other case, for the SN1, there has to be stability of the intermediate, yeah? Something like that one. So there is the stoichemical evidence. And in this case, you're going to say, if there is stoichemical evidence, if it's going to be SN2, then the product is going to be what? Is going to be optically active. You understand what you mean by optically active? You put it in a polarimeter, and then if the product is going to turn the plane polarized light either to the right or to the left, then you know you have actually formed what uh, a stereoisomer as opposed to a racemic mixture, which you're going to get with something like the SN1, yeah? Are you getting something like that one? So from the stoichemistry, if you're going to be forming products which are going to be stoichemically active, then you're going to know, hey, this reaction proceeds via this mechanism, as because this mechanism does not give products with stoichemistry. Yeah. So stoichemical evidence can give you direction as to the mechanism which you are likely to actually follow. Then before I really come to this one, let me mention something about kinetic isotope effects. Yeah, this one you're going to be mentioning later, but what you're going to say is that just to mention before we really come to that one, if the mechanism is going to involve probably if the carbon hydrogen bond is if the uh, if the carbon hydrogen bond is going to be breaking in the rate determining step, then the rate uh, uh, is going to be enhanced in a certain type of reaction relative to you replacing uh, that hydrogen with deuterium. Deuterium and hydrogen are supposed to be reacting in a similar manner because these are isotopes of the same atom. But uh, uh, the mass is going to be different, and then what you're going to see is that there's going to be a difference in the reaction rate if you're going to have hydrogen, if you're going to replace hydrogen with deuterium, yeah. So there is the kinetic isotope effects in which if you're going to replace especially hydrogen with deuterium, then you're going to get completely different reaction rates if if the carbon hydrogen bond breaking is the rate determining step. But that one you're going to come to later. And this is something which is useful in telling you information about a certain mechanism taking place. Now, in a short while, I've mentioned something about reaction rates, but once again, um, This is something which you are likely to do to determine a mechanism. Excuse me. It's something which you can easily set up in a laboratory, in an experiment. Very simple, and it can give you information about a mechanism. You're going to say maybe this reaction uh, is dependent on this reagent. Eh? In that case, you've got to ensure that you hold the concentration of the other reagents which you think are not reacting constant, and then you vary one of the reagents. If the reaction rate is going to be enhanced as a result of you probably doubling the the reagent which you think is actually affecting the mechanism, the the reaction rate must change proportionally to the concentration of this reagent. But if it's not, then you're going to say it is zero order relative to that reagent. And then what you're going to say is that the reaction order is going to be a sum of the individual orders. Anyway, you're going to really come to that, but in general, a reaction can either be said to be first zero order, first order, or second order. And and what you're going to see is that uh, there's some equations that you are going to really give to you, but I think those equations are in the previous. I think it must be kinetics too. Yeah, there are those equations that you are going to be uh, to use. In one case, a plot either if it's just going to be a concentration plot against time, then if there's going to be something like a linear relationship, then you're going to say, hey, probably going to be zero order. If a natural log of concentration via uh, certain aspect of like time and the rest, then you're going to say, hey, probably I'm going to get what first order, and probably there's the reciprocal of but anyway, let me leave it upon that one because you're going to be looking at this one, yeah? So that in this case, you can be able to say this reaction proceeds via this mechanism because this reaction is actually been shown to be dependent on this reagent, yeah? So the reaction rates can give you definite information about the reaction mechanism. So what we're going to do is that I'll mention uh, that this topic on mechanisms and ways of determining them, you'll find in this book on March. It's written MARCH. That is March. Yeah, in the Google Docs reference document, Jerry March. Yeah, it's called Advanced Organic Chemistry by Jerry March. So chapter 6 is on mechanisms and ways of determining them. So you just look at that one. A lot of this information is contained in that chapter. I think if it is the same book that I'm dealing with, it's page 296. That's at the bottom as it's written. I'm saying that because something like PDF, like uh, Adobe Reader may show a different page number at the top, but the one at the bottom may be a bit different. But if you're going to be looking at the page at the bottom, then it's written page 296. But if you're going to be seeing like the one at the top, because it takes into consideration like the indexing like from the table of contents and the rest, then I think it's page 314. Yeah, but I prefer to go with the page at the bottom. Yeah, it's page 296. Jerry March, Advanced Organic Chemistry, Chapter 6. So look at that one, and it gives very specific information about this this topic here, mechanisms and ways of determining them. So in a short time, we'll be looking at uh, weak acids and ionization. So that one will lead to us looking at equilibrium constant, and also the derivation of the seeing the relationship between pH and then another physical property called the pK. You're going to see how you can derive it. Yeah. So we are now be looking at ionization constants, weak acids, and the rest, and the information you can get from that one. So that from there we'll come back later to the reaction rates and and we'll go to more advanced ways of reaction rates by studying things called steady state approximations, because some reactions may not be just simple like that. You're going to see a reaction may proceed through one intermediate, that intermediate goes to another intermediate. You're going to see what you're going to do to try to simplify those equations. Is that okay? Yeah. So let me stop there. As I mentioned, you look at this chapter in Jeremiah chapter 6, mechanisms and ways of determining them. Chapter 6, that is page 296. So I really hope you've really enjoyed this short lecture session on mechanisms and ways of determining them. Okay, thank you very much.